Welcome to Lecture 3.6, Variation of Parameters. The name of this lecture should sound familiar because we've seen the first order analog of this method. So let's summarize first the methods that we've seen for solving first order equations. So first of all, if our equation was homogeneous, something like y prime equals a of t y, if we had an equation like this, then we could separate variables. Remember, we wrote dy dt equals a of t y, and then dy over y equals a of t dt, and we integrate both sides and keep going. Now, if the equation was not homogeneous, then we could use the integrating factor method. Recall that happened when, our example was that when we had y prime plus a of t y equals f of t. In this case, we take this thing. Actually, I should probably circle the plus sign as well. I don't need to. Yes, and then the integrating factor was, well, I'm not going to write it like that. I'll write it like this. So the integrating factor was e to the capital A of t, where capital A I mean the integral of this, and then we multiplied this entire equation by that integrating factor, and then we could do the product rule in reverse. Now these two methods do not work for second order equations at all. These things are, these don't work for second order. And there's no real generalization of them either. However, these next two methods do work for second order. So undetermined coefficients and variation of parameters, both of them have the same first step. Solve the related homogeneous equation. So in undetermined coefficients, that's the one where y of t equals the homogeneous solution plus the particular solution. So the first thing to do is to solve the homogeneous equation, which you do by separating variables. And then you have to somehow cook up a particular solution. You got to do it by inspection. Now you can't always find a particular solution, in which case, well, you've done this far. You've solved the homogeneous. Instead of going back and using the integrating factor method, you can use the variation of parameters method. You can look for a solution, yp of t, to be yh of t times, I'm sorry, not yp of t again, times v of t, and then solve for v of t. And that's the variation of parameters method. Really what it did is it was a method for finding a particular solution when you needed one. So in some sense, these can be combined into, both of them have the same idea. Homogeneous plus particular is just, this is one where you can do it by inspection and, well, a little bit of work, and this is a surefire way that's always going to work. So for second order ODEs, again, these two were out of luck. This method, when we're lucky and when our particular solution has a very nice form, we can certainly guess it, as we've seen. But in general, that's not always going to be the case. And so the variation of parameters method is going to work. And it not only works for second order, it works for nth order. And actually more than that, it works for n by n systems of first order ODEs. So to compare the first order and second order methods, the variation of parameters method works for first order. You guess the particular solution is some function times the homogeneous solution. And for the second order, well, you have your homogeneous solution is going to have, in this case, it's going to be yh of t equals c1 y1 plus c2 y2. So you guess that your particular solution is going to be v1 times y1 plus v2 times y2. And then you can guess what's next. Next, you need to plug this thing back into your equation. So let's maybe write this. So suppose you have y double prime plus, let's say, A of t y prime plus B of t y equals f of t. So you assume that your solution has this form. You take derivatives and you plug it back into here, and it'll show you that this will always work. You can always find a v1 and v2. Let's dive in with an example right away. So find a particular solution to this equation. So the first thing to do is to solve the homogeneous equation. That's easy. That's yh of t equals c1 cosine of t plus c2 sine of t. So I'm going to let this be y1 and this be y2. So let me write that out. y1 of t equals cosine, and y2 equals sine. Okay, so the first step, of course, is to assume that there is a particular solution, yp of t, of the form v1 cosine of t plus v2 sine of t. Okay, now let's take derivatives of this. So yp prime is going to be v1 prime cosine of t minus v1 sine of t plus v2 prime sine of t plus v2 cosine of t. So what I'm going to do is I'm going to collect the terms that have a v prime in it together. So I'm going to write this as v1 prime cosine of t plus v2 prime sine of t. Put those together. And then I'm going to write the remaining terms, v1 sine plus v2 cosine. Now there's probably going to be a lot of v1s and v2s that work for this. So what we need to do is we need to find v1 and v2 that are actually pretty simple enough that we can actually solve the equations. So it turns out that, so we're going to have a lot of degrees of freedom, that we can actually set this whole thing equal to 0, and we're still going to be able to find solve for yp. So we're going to set this thing equal to 0. And it's not clear why this is going to work. It's not clear that, are we asking for too much? Is there necessarily a solution where this whole thing is equal to 0? Turns out, yes, there is. So why I want to do that is because now that will set yp prime equal to negative v1 sine of t plus v2 cosine of t. So this is yp prime. Let's keep going. Let's take the derivative of that. Yp double prime is negative v1 prime sine of t minus v1 cosine of t plus v2 prime cosine, let's fix that, v2 cosine of t minus v2 sine of t. Okay, now again I want to group these v primes together, so I'm going to write this as, you'll see why shortly, as negative v1 prime sine of t plus v2 prime cosine of t minus v1 cosine of t minus v2 sine of t. So this is yp double prime. So let me box this. So now what we want to do is we want to plug back in. Maybe I should have boxed that in blue. Because we have yp prime and we have yp, and we need to plug that in to this equation. Okay, so let's do that. So let's plug in y double prime plus y and set that equal to tangent. So yp double prime plus yp, what is that going to give us? So that's going to give us, let's write y double prime first, negative y1 prime sine of t plus, not y, v1 prime, v2 prime cosine of t minus v1 cosine of t minus v2 sine of t. So that's yp double prime, and then yp, that's up here, plus v1 cosine of t plus v2 sine of t. And look what happens. You see something here? That term is going to cancel with that term. And yes, that always happens. So let's simplify this as negative v1 prime sine of t plus v2 prime cosine of t. And what does that equal to? That equals tangent, right? So this is tangent of t. So now what? So now I claim we have a system. We have this equation. I'm going to box this. And what else do we have? We have this equation involving v1 prime and v2 prime, and we also have this equation involving v1 prime and v2 prime. So, yeah, these two equations is actually going to be a system of first-order differential equations, which I know we haven't learned how to solve, but in this case, we'll see. This is one of the special cases where we can solve it. So let me write that up here. I'm going to use this area up here. So we have v1 prime cosine of t plus v2 prime sine of t equals 0. That's our first system. That's our first equation from here. And our second one's going to come from here. So we have negative v1 prime sine of t plus v2 prime cosine of t. And I know that looks like a u, but that's a v2 equals tangent of t. So this system, if we want to, we can write it in matrix form. Now let me just mention that. I'll mention several things about this. First of all, I'll mention that if we wanted to, we could write this as v1. No, I don't want to say v1. Actually, let's make myself some space here. We could write this as cosine of t, sine of t, negative sine t, and cosine of t times v1 prime, v2 prime equals 0 and tangent of t. Just barely fit that in. And this may seem a little random now. Why did I do this? But notice what these entries are. This entry, this is y1, this is y2, this is y1 prime if you include the negative sign, and this is y2. So yes, in general, you do get a system. v1 prime y1 plus v2 prime y2 equals 0. And then another one, v1 prime y1 prime plus v2 prime y2 prime equals 0. So yes, you do get a system like this, and that will always happen. In the next example, we'll actually do this for general second-order equations. So to summarize what we've done before, we are looking for a particular solution, just one, to this equation here. So we assume there was one of the form v1 cosine plus v2 sine, and then we plug this thing back in, and we got this system. Now this cosine and sine, this came from the fact that cosine and sine solve the homogeneous equation right here. So we don't know how to solve systems of ODEs yet. That's something that we will study in the next series of lectures. However, even there, we don't learn how to handle the cases when the coefficients are variables. We only study the case when they're constants. So that's beyond the scope of this class, and in general we don't know how to do it, but in special cases we can solve for v1 and v2 explicitly, and that's what we'll do here. So notice that this is a very special system, because if I multiply this top system by sine and this bottom system by cosine, then I can add these two equations and the v1 primes get eliminated. So let's do that. So let's write this as how do I want to write this? I want to write this as sine of t times cosine of t. Let's add these things up. And now look what's going to happen. These first two terms are going to cancel. And we're going to be left with v2 prime times sine squared plus v2 prime times cosine squared equals tangent. So let's write that down. So that's v2 prime times sine squared of t plus cosine squared of t. Oh, I said tangent. That's not quite right. It's cosine times tangent. Don't forget to stick that onto here. So cosine times tangent is sine of t. So this thing, of course, is equal to 1. So this whole equation simplifies to v2 prime equals sine of t. Okay. So that's v2 prime. Let's do the same thing and isolate v1 prime, I should say. So instead of multiplying by sine and cosine, we want to eliminate this. We want these to cancel. So let's multiply this first one by cosine and the second one by sine, and then subtract these two equations. So let me write that down here. So we're going to take v1 prime cosine of t plus v2 prime sine of t equals 0. And let's write the second one first. Negative v1 prime sine of t plus v2 prime cosine of t equals tangent. And we want to multiply the first equation by cosine and the second equation by sine. And then we want to subtract these two. So let's put a negative sign here. So if we subtract these two, what happens? So these two terms will, oh, I said subtract, yeah, so these two terms will cancel. So if you think of the negative sign, put the negative sign here and then add them. So subtracting this equation without the negative sign from that is just adding these two things with the negative sign. Now, the v1 primes, what do we get? We get v1 prime times cosine squared of t plus sine squared of t. And now we have 0 minus sine t times tangent, so that's going to be, what's sine times tangent? That's minus sine squared of t over cosine of t. So of course this thing is equal to 1, and we get our second equation. Let me put it up here. v1 prime equals negative sine squared of t over cosine of t. Okay, so let me fix that a little bit. Cosine, and that is sine squared. Okay, so this first one we know how to integrate, and the second one, In Calc 2, you were expected to know how to integrate that. I don't need you to know how to do this right here. Use a computer. That's what they're for. Yeah, Calc 2 was like a hazing. It's like, here's all these integrals that most of them you'll never see again, but you got to do them. And once in a while you see something like this. Okay, so this one does come up, but we have computers. Okay, so let's solve this. So v1 turns out to be negative natural log of secant t plus tangent t plus sine of t, and v2 turns out to be negative cosine of t. I should probably add plus c and plus c. However, we're not looking for the general solution. We're just looking for any one particular solution that works. We just want one. So we have the liberty to take this c and just make it anything we want to. Let's make it 0. So let's get rid of that, and let's get rid of that. So now we have our v1 and v2. We have our particular solution. So yp of t equals v1, which is negative natural log of secant of t plus tangent of t plus sine of t times cosine of t plus v2, which is minus, so maybe I should say minus v2 times sine. So that's minus cosine of t times sine of t. So this is our particular solution. Let's box this. And then, well, that's all I asked to find a particular solution. The general solution, of course, is y of t equals yh of t plus yp of t, which is c1 cosine of t plus c2 sine of t plus yp of t. So if you wanted to, you could, I'm not going to copy this whole thing just for the sake of it, but if you wanted to, you could factor out a cosine, and you could say that the general solution was cosine of t times this thing plus c1 plus sine of t times c2 minus cosine of t, if you wanted to. Actually, yeah, let's do that. Let's just so you can see a different form. So y of t equals cosine of t times c1 minus c1 minus natural log of secant of t plus tangent of t plus sine of t plus sine of t times c2 minus cosine of t. So you can see why undetermined coefficients is not going to work. There's no way you would have ever guessed a solution like this to this dinky little ODE. Okay, so let's consider a very general case when our forcing term is just some function f of t. Not only that, but the homogeneous part doesn't even have to have constant coefficients. So we actually haven't even seen how to solve homogeneous equations where these terms a and b are functions. We will see that in the remaining 3 lectures of this section. But let's just suppose now that we had a solution to the homogeneous equation. So let's suppose that yh of t is c1 y1 plus c2 y2. Then, as before, we are going to look for a particular solution of the form v1 y1 plus v2 y2. Okay, so I'm going to go through this a little bit quickly because it's similar to what we did before. So yp prime is v1 prime y1 plus v1 y1 prime plus v2 prime y2, just doing the product rule a few times, v2 times y2 prime. And as before, I'm going to group the things with the v primes in them together. And the reason for doing this is because the reason why it worked before is because we didn't have any v1 or v2 primes. If we had that, then that system idea would not have worked. So we're going to write v1 prime y1 plus v2 prime y2 plus v1 y1 prime plus v2 y2 prime. And as before, this is something that we are going to ask to be equal to 0. And it will work out that we can assume that that is equal to 0. Not clear a priori, though. Okay, so if that thing I boxed is equal to 0, that means that yp prime equals v1 y1 prime plus v2 y2 prime. So we take another derivative, and we say yp double prime equals v1 prime y1 prime plus v2 prime y2 prime plus v1, I know I'm going a little bit fast, v1 times y1 double prime plus v2 y2. I know I'm going is it a little bit fast, but all I'm doing, I'm just taking derivatives. I'm just doing the product rule on each of these things. So this is yp double prime, and so now we need to plug these things back into the equation. So we need to take we need to plug this thing back into there. We need to plug this thing back into here, and we need to plug this thing back in to there. Okay, might get a little messy here, but I think we can handle it. Yp double prime plus a of t yp prime plus b of t yp is, so let's just copy these things down here. So it's this thing plus a times this plus b times that. So that's v1 prime y1 prime plus, again I'm going quickly because it's just busy work, v2 y2 prime plus v1 y1 double prime plus v2 y2 double prime times, no, not times anything, plus, actually I can fit this, oh, let's keep it down here, plus a of t times this creature times v1 y1 prime plus v2 y2 prime plus b of t times this, b of t times v1 y1 plus v2 y2. Oops, I can write that a little bit neater. It's v2 y2. Okay, now what? Let's what do we do now? So what do we have here? This whole mess. We have v1s, we have v2s, we have v1 primes, and v2 primes. So let me write that as such. So let's see. So we have how many v1s do we have? So v1s, we have a, where's the v? We have a y1 double prime here. We have an a times y1 prime here, and we have a b times y1 here. So that's nice. So what was that? That was v1 times y1 double prime plus a of t y1 prime plus b of t times y1. What does that look like? That looks just like that, which is f of t. Nice. Okay, so plus, how many v2s do we have? v2, oh, I said that, wait, I'm sorry, that's not f of t. Y1 solves a homogeneous equation. So when we plug this thing back into here, we get 0. Okay? So bear with me. So we have v2 times, how many v2s do we have? We got a v2 here, y2 double prime, y2 double prime. Where's another v2? We have a v2 right here, y2 prime times a, plus a of t, y2 prime. And then we have v2 times y. So, oh, and of course there's a b out here, so plus b of t times y2. Okay, so we have those things, and now what do we have? Now we have, well, so what's left in this mess? We have terms with y1 prime and terms with, sorry, v1 prime and terms with like a v2 prime. Where the heck is a, there's our v2 prime. So plus y1, or v1 prime, y1 prime, that's just, so there's one term, and there's the other term. Plus, oops, I didn't mean to make that red, but plus v2 prime, y2 prime. So it looks like a mess, but a common theme of variation of parameters is everything cancels, or almost everything cancels. So as before, this thing here, y1 solves the homogeneous equation, which means when I take y1 and I plug it in the left-hand side, I get 0. So that means that this whole thing is 0, as is this. This thing is 0. So here's what we're left with. And what does that equal? We're taking our particular solution and we're plugging it into the left-hand side. It better equal f of t. Right? So this thing equals f of t. So let me box this equation. So now we have this boxed equation, and we have this boxed equation as well, being our two, well, the same thing that we had before. Let me write that. Where do I want to write this? So we got a system. Oh, I can't spell system today. That's why. So we got a system. This first equation up here, we write this as v1 prime y1 plus v2 prime y2 equals 0. And then down here, we get the same, well, v1 prime y1 prime plus v2 prime y2 prime, not quite, but equals f of t. So this thing, amazingly, it always works. There's a system that we get. And now we've reduced finding a particular solution to solving this system. And we're going to proceed just like we did in the special case in example 1. So to summarize so far, if we can solve the related homogeneous equation to this, where we set this equal to 0, then we assume that there's a particular solution of this form, v1y1 plus v2y2, and we plug that back in, things massively canceled, and we get a system like this. Now in matrix form, which I want to get you warmed up to the idea of, we've seen it a little bit before, we can write this as, this is y1, y2, y1 prime, and y2 prime times v1 prime, v2 prime equals 0 and f of t. So it's not clear when this equation is always going to have a solution, but it turns out that it depends on this matrix right here. So I'm not going to say much about the theory of systems here, and this matrix is actually something that we are not going to see in our study of 2x2 systems, because as I said before, we're only looking at them when when these things are constants, which this will not be. But in general, this matrix here is called the Wronskian, W-R-O-N-S-K-I-A-N. It's often N, not M. The Wronskian. And this system, or let's call this W, the Wronskian W, and this system has a solution if and only if this matrix has a certain property. And if the determinant, you'll learn more about this in the next series of lectures, determinant of W is non-zero. So what is the determinant of this? So it turns out that it is this cross product minus that cross product. So i.e. if y1, y2 prime, so let me just write like this, that's if this product minus that product is 0. So if y1, y2 prime minus y1 prime, y2 is non-zero. So you don't need to have what the Wronskian is memorized. Every case you're going to see, this is going to have a solution. And the reason why is, in layman's terms, is because y1 and y2 are truly distinct solutions. One of them is not a scalar multiple of the other. And in fancy terms, that just means that this product minus this product is non-zero. Kind of trivial for 2 by 2, but it's definitely important when you have 3 by 3, 4 by 4, and higher order systems. Anyways, what was I saying? This has a solution. You can solve it the same way as you did before. So what did we do before? So we took this first equation and we multiplied it by. Remember, we wanted to eliminate v1s, so we multiplied this first equation by y1 prime and the second equation by y1, and we subtracted them, and then you solve for v2. That wasn't bad. And then you again, so you can do this. I'm not going to actually do this, all the details. And what you can do is you can take this same equation. Let me write it down. So instead of doing it out, I'm going to write down the other thing to do with it. y1 prime, or sorry, v1 prime y1 plus v2 prime y2 equals 0, and v1 prime y1 prime plus v2 prime y2 prime equals f of t. So instead, if you multiply, if you said you want to get rid of these terms, you multiply this top term by y2 prime and this bottom term by y2, and you subtract. Then you eliminate y2 and you solve for y1. So remember how when we studied integrating factor, I said here is the general formula, but don't memorize it, just learn the process. Same thing here. Learn the process, don't memorize the general formula, because it's not hard to show that the general formula is v2 prime. So v2 prime is y1 times f over this determinant, which is y1, y2 prime minus y1 prime, y2. So when you do this elimination and solving for v1 prime and v2 prime, you end up dividing by this, and that's why it can't be 0. If this thing is equal to 0, then you can't solve for v2 like this. And then you get that v1 is negative y2f over y1, y2 prime minus y1 prime, y2. So what this means is that v2 is the derivative, the integral of y1 of t, y2 prime of t minus y1 prime of t, y of 2, is that a 2? I can do that better, y2 of t times y1 of t, f of t, dt. and y1, or v1. v1 is the integral of y1 of t, y2 prime of t, minus y1 prime of t, y2 of t on the bottom, and on the top we get negative y 2 of t times f of t dt. So to summarize, here's a general linear second order differential equation, and this will have a particular solution of this form, where y1 and y2 solve the homogeneous equation, v1 is this integral, and v2 is this integral. So you're not guaranteed that you're going to actually be able to evaluate these integrals, but in the case that you are, you have a particular solution and therefore your general solution, assuming that you already have the homogeneous solution. And this thing looks messy, but this bottom thing is just the determinant of this matrix. You take y1, y2, y1 prime, y2 prime, and you take this strange little cross product. You take this product minus that product. So if this is w, then this term down here is the determinant of w. We'll study this a lot more in the next section. It's abbreviated the determinant, or det, of w. So our general solution in that case is the homogeneous solution plus the particular solution as expected.